Solving a system of equations using the elimination process is just that. You are going to eliminate a variable. So the form in which this works best for is really when no variable is isolated. In other words, they all have coefficients, or they're all on the same side of the equal sign. So the steps in doing this, what you want to do is you want to line up the like variables and the equal to sign. Once you line those up, you want to match coefficients. And coefficients are the values or numbers in front. Now, in order to match them, you may need to multiply by a value. And we'll illustrate that here in just a minute. Once you get them to match up and align, you want to add or subtract. And this will eliminate. And you want to eliminate a variable. You want one of those variables to go away, so you only have one remaining. Once you eliminate a variable, you want to do that back substitution, and then solve to find the second variable so you have your ordered pair. And lastly, make sure that you check your answer. Make sure you haven't made an error in this process. So taking a look at the equations. There's no variable by itself, so substitution method is not very convenient. What I'm going to do is I'm going to look at this as an addition problem. My variables are aligned, as well as my equal sign. Going straight down, adding 2y plus 3y is 5y. Adding the x column, negative 5x plus 5x, cancel. Negative 1 plus 11 is 10. Dividing by 5, y is 2. Now I need to find the remaining coordinate, the x-coordinate, so I back substitute. Really doesn't matter which equation you put back substitute in. We'll just do the first one. 2 times my y minus 5x equals negative 1. So 4 minus 5x, negative 1. Moving 4 to the other side. Negative 5x is negative 5, therefore x is 1. So it looks like my ordered pair is 1, 2. We need to check this. Going to the first equation, 2 times y, so that would be 2 times 2 minus 5 times 1. Is that in fact negative 1? Yes, it is. So I've checked my answer, and it works. So this system graphically would have one solution, and it would intersect, or those two lines would intersect at 1, 2. Looking at the second scenario, this one, my variables are aligned. It doesn't matter the order, as long as they're lined up, the equal signs are lined up. But if I was to add this, 3 and 3 do not cancel. So in this first problem, I did addition. I think in this problem, I better do subtraction. When you subtract, you need to make sure that you are subtracting both columns. 2x, take away 1x. Notice there's a 1 there. Leaves me a remaining x. 3y, take away 3y is gone. 4, take away 5. What I sometimes like to do, because I think addition is easier, I just distributed that negative sign through. And I found my solution for x to be negative 1. Now I need to back substitute. I'll just go again to the first equation. I plug in the x-coordinate in hopes to find the y-coordinate. So I'm solving this two-step equation, adding 2 to both sides. 3y is 6, therefore y is 2. So it looks to be that the solution to this system, the point of intersection, if I was to graph those two linear functions, would be negative 1, 2. Let's just double check it. Let's plug into my second equation, negative 1 and 2. X was negative 1, y is 2. Let's check to make sure that is going to be equal to 5. Notice it's positive 5 because I don't want those negatives on there. It's x plus 3y equals 5. and negative 1 plus 6 is in fact 5. So it checks. This would be the point of intersection when I was to graph those two linear equations. Let's try one more. Notice my variables are aligned. My equal sign is aligned. I wouldn't really want to do substitution method because to isolate a variable would be kind of a lot of work and probably involve some fractions. So what I want to do is make these values become the same. So what I'm going to do is I'm going to essentially put the first equation on the copier and I'm going to multiply it by 3. I'm going to take this equation and enlarge it 3 times itself. It's going to be the same, but it's going to look different. It's going to look larger. And then it gives me 9x plus 6y equals 48. Now notice the numbers are larger. All I did was enlarge them. Why would I want to do that? Well, I'm going to take the second equation and I'm going to multiply this by a 2. So I'm only going to double its size. So doubling each and every value in the equation just takes everything and multiplies it by 2. Now hopefully you can see here that I have not just arbitrarily selected 3 and 2, I've selected them such that when I use the elimination method and add up the y's, they're going to eliminate. 9 and 4 is 13x equals 48 minus 22 is 26. So therefore x is 2. Now that I know x, I'm going to back substitute. I really have 4 equations that I can back substitute my 2 into. My 4 equations are my original 2 and my 2 enlarged equations. Again, I'm just going to go to the first equation and I'm going to take 3 and multiply it by 2. So again, this process is going to use the substitution, the back substitution, to find my y coordinate. Taking 6 off from each side, 2y is 10, therefore y is 5. So again, it looks like I have a solution. It looks like these two lines, if I was to graph them, would intersect at 2, 5. Just checking, I'm going to put 2 and 5 into my second equation. Because the 5 came out of my first, I'm going to plug them into my second equation and just double check that this ordered pair works for that equation as well. 4 minus 15 is negative 11, and that's a true case, so this therefore is the solution to that system. Visually, it would be the ordered pair in which those two lines would intersect.